Good morning, students. Today we are going to discuss about the black body spectrum, and we are also going to discuss the Wien's displacement law, which is based upon these observations. So, what is perfectly black body? We know a body which absorbs all the radiations incident upon it. It is called as a black body, and it also emits the radiation when get heated. So here we are going to discuss the energy radiated per unit time per unit area by the black body versus the wavelength. What is wavelength? Wavelength is nothing but the property of the waves by which we can determine the color of the radiation. So here we are going to discuss about the graphical representation of the energy radiated per unit time per unit area versus the wavelength. Now, what are the observations of this graphical representation? Before that, we know the energy radiated by black body is totally depend upon the temperature. Now, as the temperature is low, the heat radiation emitted is less, and as the temperature of the body, perfectly black body, increases, it start emitting more heat radiation containing the mixture of the wavelengths. So, here heat radiated is plotted against the term wavelength. And what are the observations of this graphical representation? So we are starting here. The first observation is that the energy distribution of a perfectly black body is not uniformly distributed. Not uniformly distributed means if we see the graph, this graph is not uniform. So we can say that the energy radiated per unit time per unit area is not distributed uniformly at a given temperature. Now, what is the second observation? State that the energy radiated per unit time per unit area emit the radiation of the maximum wavelength at the particular temperature. Here we saw that there are four graphs, a graph at 3000 Kelvin, 4000 Kelvin, 5000 Kelvin, and this is the 5500 degree Kelvin. So we see that as the temperature increases, the area under the curve also get increases. So as the temperature of the perfectly black body goes on increasing, it start emitting the more radiation having mixed wavelengths. As we see, as the wavelength increases, the heat radiation goes also on increasing, and after some time it reaches a maximum value and then also start decreasing. So the wavelength which is corresponding to the maximum intensity of the radiation emitted, the maximum intensity emitted is denoted by for particular wavelength denoted by lambda m. It is the property of the perfectly black body. Now, as we see, as the temperature of this graph, temperature of the perfectly black body goes on increasing, the peak of this graph shifting towards the shorter wavelength. This is shifting towards the shorter wavelength. So we can say that as the temperature increases, this maximum wavelength, what is this maximum wavelength? This maximum wavelength denotes the radiation of the maximum intensity, and this value goes on decreasing as the temperature goes on increasing. So what is the area? The area under each curve goes on increasing. As the temperature increases, for example, for 3000 Kelvin, the area under the curve is very less. But as the temperature goes on increasing, the area under this curve is increases, which is show that more amount of heat radiated per unit time per unit area. So this is about the energy distribution, energy black body energy spectrum maximum, which is plotted against the energy radiated versus the wavelength of the heat radiation. Now we are going to move towards the Weiss displacement law. What Weiss displacement law? In this graph, we study that as the temperature increases, this lambda m, the maximum wavelength for which the heat radiation having maximum intensity is shifted towards the shorter wavelength. So we can say that the value of lambda m, decreases as the absolute temperature goes on increasing. So what is the conclusion from that? We conclude that this absolute temperature and this lambda m, they are inversely proportional to each other. So we can write here this lambda m is inversely proportional to the absolute temperature, that is lambda m is inversely proportional to T, absolute temperature. So we can write here this lambda m is equal to B by T, where this B is Weiss constant and whose value is given in the book, which is equal to 2.897 into 10 to the power minus 3 meter Kelvin. Now, what is the application of this Weiss displacement law? Using this Weiss displacement law, we can determine the temperature of the distant stars, for example, sun, dwarfs, or the giants, astrology. So we can say that by using this Weiss displacement law, we can determine the temperature of the sun also. We learn about the white dwarfs and red giants, which state that white dwarfs has a temperature, surface temperature about 10,000 Kelvin, and red giant, they have about temperature 3,000. So if we see by using this Weiss displacement law, we can also determine the surface temperature of the white dwarf and the red giants. At the less temperature, the color emitted by the bodies, astrologer bodies, they are in the red. But as the temperature goes on increasing, its color changes and it becomes white. It is the mixture of the all colors. So as the temperature goes on increasing, the wavelength goes on decreasing. The wavelength of red color is maximum, and as we increase the temperature, the wavelength goes on decreasing. So this is the Weiss displacement law. By using this displacement law, we can determine the surface temperature of the very long situated stars, for example sun. Now we are going to discuss about the next law, which is nothing but the Boltzmann law, which gives the relation between the emissive power of the black body and the absolute temperature of the black body. So what is the relation? What is the law? Boltzmann. What is Boltzmann law? Stephens and Boltzmann law derive or give the relation between the emissive power of the black body and the absolute temperature. Now, what is the relation? What is the formula for that? The formula states that the radiant power emitted is directly proportional to the fourth power of the absolute temperature. So, what is the emissive power of the black body? It is denoted by RB, which is directly proportional to the fourth power of the absolute temperature of the black body. Now this is Stephen's sigma multiplied by t to the power 4, where this sigma is nothing but what? It is nothing but the Stephen's constant. Okay, and this Stephen's constant value is nothing but Stephen's constant value is given by 5.67 into 10 to the power minus 8 watt meter inverse 10 to the power minus 4. This is the value of Stephen's constant. So we can write this RB is equal to sigma into T to the power 4. But this value or this relation is for the perfectly black body. Now, if we have to derive the relation for the ordinary body, then we know that what is the emissivity power of the black body is equal to R divided by RB at a given temperature. So we can write that this R is equal to E multiplied by RB. What is E is the coefficient of emission and this RB is the emissive power of the black body at the given temperature. So we can write here is equal to E multiplied by sigma multiplied by T to the power 4. This is the Boltzmann law in the case of ordinary bodies. Now, if we have given a surrounding temperature that is equal to T0, then, for example, a perfectly black body having the absolute temperature T is kept in a surrounding having temperature T0. Then, what is the energy emitted? The energy emitted is directly proportional to sigma into T to the power 4, and the energy which absorbed is equal to sigma into T0 to the power 4 by the perfectly black body. What is this? This is the energy emitted by the perfectly black body, and what is this? This is equal to the energy absorbed by the perfectly black body when it is at the surrounding temperature T0. Its absolute temperature is equal to T. Then what is the energy lost by the perfectly black body? Then this energy loss is equal to sigma into T to the power 4 minus T0 to the power 4. This is the amount of energy lost by the perfectly black body when its absolute temperature is T and the surrounding temperature is T0, provided that this T is greater than T0. If a condition arises that this T is less than T0, then this equation becomes this sigma T0 to the power 4 minus T to the power 4. Okay, this is the relation for the perfectly black body when the temperature of the surrounding is greater than the body. In this case, the energy is gained by the perfectly black body, and in this case, the energy is lost. So, this is the relation in the terms of surrounding temperature for the perfectly black body. Then what for the ordinary body? For ordinary body, we can represent this equation as energy loss or energy gain is equal to E into sigma into T to the power 4 minus T0 to the power 4. So this is the relation in the case of ordinary body when we have given the absolute temperature of the black body and the surrounding temperature of the black body. So today we discuss about the black body spectrum, then we discuss about the Wien's displacement law, and then we discuss about the Stephen's Boltzmann law. So in this way this chapter ends here. In the next lecture we are going to start a new chapter which is nothing but the thermodynamics. So this is for today. Have a good day. Bye.